Hello dear friends, I'm glad you make it to our second lecture. Now look at this beauty. This is just a picture from my house last week. I took it last week. Now you may wonder why everybody, actually the majority of population of the all the world population, it's living in the coastal cities, in the coastal places. And you may wonder why so. And obviously something has to do with water. First, the climate is milder where the people are near the water, and we're gonna understand why. We're gonna learn why. And then after the site, just look at this site. It's just incredible. It looks so beautiful, and the rhythmical noise of the waves, it has a calming effect also. It is so nice. And also for me personally, the sea gives me the feeling that something is infinite, because you see the horizon, but you know that there is something behind the horizon. And also you can see something is moving, and actually you can see something, it's like moving and infinite, and that gives you a great feeling and great sensation. And obviously all God's creations are showing to God, and this makes us appreciate it more, as we stated in our previous lecture. Now let's revise quickly what we learned in our previous lecture. Now there was 4 important laws. The first law, Lavoisier, which stated that the mass is preserved. So water and iron makes rust and hydrogen gas. Of course, the iron must be hot, and the water must be at steam state, must be in a vapor state. So it shows that the reactants mass and the product mass is the same. This is the law of conservation of mass. Then came Joseph Proust and says that all the compounds are combined with certain ratios which are definite. The compounds that he studied, the metals, he found that the elements in the compounds are combined in these compounds into a definite proportions. They've got definite proportions. So doesn't matter where you take the water, doesn't matter how do you produce the water, through chemical reaction, through burning hydrogen, that's how it's gonna, as we're gonna learn in this lecture, or you take it from different places or from different states. Always the proportion of mass of hydrogen to oxygen is the same. We've got 2 mass units of hydrogen, and we've got 16 mass units of oxygen. Wherever we've got 1 molecule, or we've got 1 ton, or we've got millions of molecules. That's the law of definite proportions. And also the law of, that's the third law that we studied, the law of constant proportions. That means this proportion is going to be exactly the same. Doesn't matter the phase, is it steam or ice or liquid, always this is going to be a constant proportion. And also regardless of the volume and of the mass and whatever, always we're going to have the same proportion. And the fourth law, which is the least intuitive, is the law of multiple proportions. And the law of multiple proportions says to us that now when we've got 2 different compounds with, say for example, 2 different elements, the ratio with which they combine is with small numbers, the law of multiple proportions, which it says that the elements combine in a proportion with whole numbers, small numbers with the whole numbers, not with half numbers, not with any fractions. And we gave an example of sulfur dioxide and sulfur trioxide, and we found that 10 grams of sulfur combine with 10 grams of oxygen. But now look at it. The unit mass of sulfur, or the molar mass, you can say, we're going to study what is mole, is 32 grams per mole. Sulfur molar mass is 32 grams per mole. Mole is a quantity of molecules, 6.022 by 10 on the 23rd power, huge number. So if you've got that much of molecules of sulfur, is going to be weighing 32 grams. While if you've got oxygen, one atom of oxygen, and you've got this number 6.022 by 10 of 23rd power, you're going to have 60 grams of oxygen. All right, now we see now that they combine 10 grams of sulfur combines with 10 grams of oxygen, but the molar mass of oxygen is half of the molar mass of sulfur. That means if we combine with equal proportions 10 grams of sulfur with 10 grams of oxygen, definitely oxygen must be 2, because the oxygen is 2 times lighter than the sulfur. All right, so now we've got a proportion here where we've got 2 oxygens for 1 sulfur. On the other compound that we study, sulfur trioxide, we see that 10 grams of sulfur combines with 15 grams of oxygen. So now we've got here one more atom of oxygen, because definitely the oxygen is, as we said, 2 times lighter than the sulfur. So we've got, in the first case, in the sulfur dioxide, 2 atoms of oxygen combines with 1 atom of sulfur. The second case, 3 atoms of oxygen combines with 1 atom of sulfur under different conditions, of course. So now we've got 15 grams of oxygen in the second case and 10 grams of oxygen in the first case. In the first case, we said that we've got two atoms combining with 1 atom of sulfur, because oxygen is twice lighter than the sulfur. So in the second case, we've got 3. So we've got 15 grams. So this is the law of multiple proportions. Now, also, we found that the atom is consisting of protons, neutrons, and electrons. And we found also that the electron is not rotating on a nice, beautiful circles around the atom like Niels Bohr proposed, but the electron is a particle and a wave. So now let's look at the oxygen atom. Just look at it very, very carefully and see now the electron clouds, how the electrons are situated. They are not in a nice orbit, they're in the clouds. And also you can see the nucleus, which almost all the mass is concentrated, and you can see the neutrons and the protons. But just look at it, this is very nice animation where it shows that the electrons are in the clouds, and the probability to find the electron is exactly in these clouds, not outside of them. Now let's go to something very familiar to you, so that we can understand actually the basics, the fundamentals of the invisible that is going to make us understand the visible. See, this is how we're gonna learn it. Now we studied the atom, we studied how the atom is actually is operating, how it's working, where is the electron clouds, where is the nucleus. We studied everything now. We know it. We even revised the 4 laws. So now it's time to see how the atoms actually are, if we sort them, how they can be sorted. And 150 years ago, Mendeleev, a Russian chemist, in a dream actually looked and saw that the elements can be combined in a certain way. This is a periodic table, and the elements are combined by their atomic number. And atomic number is actually the number of protons in the nucleus. So the atomic number shows the protons, and the protons, we know very well, determine what kind of element is. So that means if we've got 8 protons, the oxygen is going to be always is going to be oxygen. There is no other element with 8 protons. That's its atomic number. Then after we got his symbol, and then we've got his name, and then we've got his atomic weight. What means atomic weight? Atomic weight means how much 1 mole of 1 atom of this substance, of this element, weighs. So you can see that 1 mole of atom, not molecule, of hydrogen weighs 1.008. Oxygen weighs almost 16. Right. So another thing that is in the periodic table is the electrons per shell. What means that? The chemistry is possible because we've got electrons that combine. If there are no electrons, like in the sun, the temperature is so high that, as I showed last lecture, when the light hits the electron, the energy hits the electron, sometimes the electron gets flight away and the atom gets ionized. So in the high temperature of the surface of the sun, 5,700 degrees, we've got only protons and electrons and nothing else. There is no molecules, very few molecules, only protons and electrons, a big soup and neutrons. All is turning around. They combine, they disintegrate. It's a huge temperature, so that this height is, that's only on the surface of the sun. Inside, the temperature is much bigger, 15 million degrees. On the surface, even on that 6,000 degrees, 5,700 degrees, you can see that there is no possible of any chemistry. And this is why the sun is not burning with chemical energy, like we're going to learn how the hydrogen burns with oxygen and creates water. You see, or like you burning a methane gas on your gas stove. You put the gas, there is oxygen in there, and it turns into carbon dioxide, and it turns into water vapor. This is a chemical reaction which releases energy and you cook your food. But on the sun, there is no chemical energy. If you want to learn how the sun is burning, but it's not using the energy like we burning in the stove, chemical energy, then you have to look at my astronomy series. Then I explain it, how it's doing this, if you're curious enough. So, but we're now talking not astronomy, now we're talking chemistry. So the electrons per shell shows how much this element can combine, in what way it can combine with other elements. Say for example, the oxygen has 6 valence electrons. That means valence able to combine with other elements. And hydrogen got 1 valence electrons. As we're going to study later, all the elements wants to have 8 electrons in their valence shell. Right? Their outer shells, it wants to have 8 electrons. And to achieve that, the oxygen, because you've got 6, combines with 2 atoms with hydrogen, and now you've got 8. You've got it. And the elements, like the noble gases which are there, they're called noble because they don't react. Like the noble people, they don't mix with the common people, right? Noble people, they don't mix. Today we don't have so much nobility, but we've got soccer stars, we've got government official. You can't just go and say, hey, you come here. You can't. They don't mix with normal people, with common people. So this is exactly like these noble gases. They don't combine with nothing. They don't combine with nothing. And these noble gases which are there, they actually exist in their atomic state. There is only elements that exist in the atomic state is the noble gases. It's only in the atoms. Hydrogen cannot exist at atoms, immediately will react either with another element or with itself or with oxygen, whatever. Oxygen also cannot stay in the atomic state. It needs to be in a molecule. So why the elements wants to get into the molecule is going to be a subject of our discussion in this series of lectures. So now this is the periodic table, and this you can see that it's a valence shell. You've got electrons, how many you've got. It shows us how it's going to combine with other elements. You've got atomic weight. It shows us how much is going to weigh when you've got 1 mole. 1 mole is excellent proportion, because when we know that certain material weighs 18 grams, now we know we've got 1 mole, because the molar mass of the oxygen is 16 grams per 1 atom, and the molar gram of hydrogen is 1 gram. So we've got 2 grams of hydrogen and 16 grams of hydrogen, of oxygen, excuse me. Now when you combine them, we've got 18. 16 plus 2 is 18. Now we've got water. Now you can see that almost always we can actually see what is the compound by measuring his molar mass. You see? So if we've got 18 grams and we know it's a 1 mole, it's a water. Right, that's it, in a liquid phase. So this is why it's important we to know the atomic weight, the name, of course, and the atomic number. We said it's determining the how many protons you got, and determines the character of the element. Now let's have real fun. There is a periodic table, and you can see the color coding is different. Now first let me show you what states are the elements. Now if we've got to find out, say, what is the liquid in the periodic table, what the elements are liquid, we've got only 3. One is a bromine, the other one is liquid silver or mercury, hydrargyrum is called, his Latin name, and then we've got copernicum, but copernicum is an artificial element, and his period of decay is only 30 seconds. But for these 30 seconds, the scientists which created it managed to measure his reactivity and managed to measure many other things. So it's also liquid, but by room temperature. Now look at the solids. Almost all elements are solids, you see, at room temperature. And then we've got gases. This is the gases. You see, it's very few. It's like the liquid. Most of the elements in the periodic table are solids, and you've got gases, and you've got also liquids, like we said it. So now let's see the category, how we're gonna categorize them. Now let's see first the metals. Now you're gonna be surprised. This is metals, this is also metals, and this is metals. You can see also that the majority of the periodic table are metals. See, most of it are metals. These are non-metals. All these 3 are non-metals. Everything else is metals. Now there is a special category which is between metals and non-metals. There, look at it. Because of silicium we can have computers, and I can talk to you My digital camera is recording with help of the silicium, which is a semiconductor, and because of this property being semiconductor, when we force some electrons, it goes into the binary road. One is 0, another one is 1, and when we've got the bigger combination, it can actually record all my image, all what I'm saying to you. You can use your cell phone just because of this property of silicon. You got also boron, germanium, astatine, and tellurium and polonium and stibbium. Now we've got all of these elements which are not neither metals, neither non-metals. They're called metalloids. So now if we put all the system if we take it now, what we can do, you can have fun. You can press on a hydrogen and you can see how it looks. You can see its atomic weight. This is how it starts shining when we put electricity through it. You've got a configuration, nucleus and the electron. We said that this is only representative, it's not a real case. We've got this boiling point in Kelvin, melting point. You've got heat capacity, that means how much energy you need to rise the temperature with 1 degree, and many other properties. We've got the radius of that, and we've got everything. It's actually incredible, and it tells you how many of this element is abundance, when is discovered, who discovered, etc., etc. Now you can see also, you can look at the elements by their images. Look at it. What a beauty. You can stick on the element, say stick on the silicium, and you can look at it. That's the silicium which the computers are made with. You can see all other elements. All right, you can download this application, the Windows. It's called Periodica. All right, this is how the noble gases are. See, beautiful colors, beautiful. Every noble gas has a specific color when it's energized. Then we can see the oxygen also, which causes when electrical particles from the sun, charged particles, actually hit the oxygen molecule, and oxygen atoms, they get them excited, and when they return back, they emit light, like we showed you in the previous video. It shows you also the electron configuration. You can see the valence shell is 6, and we said it's very important. It tells you how much is the density, etc., etc., who discovered and which year. So it's incredible. You can actually download this and play around. Wherever element you're interested, you can click. This is gold. You can see how big is the gold atom, and what's happening with the gold atom, why it's actually such a shining, beautiful color, is when the electrons are so many, inside the electrons start turning with much faster speed than normally, because they get attracted, and because of this we got relativistic properties, and this is why we've got the color to be like this. Otherwise we would have much different. Would have looked like a normal metal. See, like say for example cadmium or palladium or whatever is gonna look like metal. All metals normally look more or less the same. Silver and shiny, all of them are looking more or less, but this beautiful color comes because of the electrons get such a high speed that they start experiencing relativistic effects, in a way that when something is moving near the speed of light, and the electron start moving with that kind of proportion of that kind of speed, it's get more heavier, and because of that, actually the atom is actually absorbing certain kind of light, and is emitting the other kind of light, and this is why you can see it is this shiny gold color, that's called. You may wonder also why mercury is liquid. You see, it's exactly the same relativistic speed of the electrons, because there are so many and they start getting heavy on the atom, and because of that, when this speed is getting very high, the electrons now cannot combine in the metal lattice. We're going to study it, what is metal lattice, cannot combine so much to press the nucleus down and keep it, and this is why it's liquid. You see, they are more loose. It's liquid at normal temperature, just because of this relativistic effects with when the electrons are getting too many and they start turning with relativistic speed. So this is the periodic table, and you can play around, you can download it, you can do it. As you can see, it's beautifully made, and we keep on adding more and more elements. I just want to tell you another thing. I love chemistry, but I don't like work as a chemist, because most of these elements and their compounds are poisons, and I don't like working in a chemical factory. That's the one thing. I don't like being chemical engineer or something working in a chemical factory. So it is dangerous. I don't like touch that. And you can see that you've got around 120 elements with the artificial ones. Now, when you've got 120 elements, now we don't have only 120 substances. Can you imagine if it was that the case? It would be a boring world. But now we've got such a variety of substances. How this variety of substances actually came into being? Very simple. The elements get combined. And when they get combined, now you can imagine what is the variety of combining 120 elements with each other with different proportions. Till this day, 30 million chemical compounds are discovered. 30 million chemical compounds. Can you imagine? Out of it, non-organic, that means not having carbon and hydrogen, without these two elements, because organic compounds got carbon and hydrogen minimum. We need to have also a different oxygen and maybe nitrogen and sulfur and so and so, and you can have different organic compounds, but non-organic compounds are those that are without these complex organic molecules. And non-organic compounds are 500,000. It's much less than the organic compounds. Organic doesn't mean that exists only in organisms, in the living cells. It exists also in the lab. They can be created, they can be discovered, but mostly they're the compounds of carbon and of the hydrogen. And as I said, it's most of the compounds are poisons. That is another proof. That's another proof that the life can exist only by God's hand, simply because it is a very narrow slit of conditions and of chemical elements that need to combine and work together so that the life can exist. Now, little chemical disbalance in your body and you're dead. Little but less oxygen and your brain stop working. Just little but not much. More of a certain chemical, like a benzpyrene, which got a very flat molecule and goes inside of DNA and cuts it and destroys certain parts, you get cancer. You see, it is a very dangerous world we're living at. Chemically we're talking about. So now, the life to exist as such, and to exist for many years, since creation is 6,000 years, we need to have a very specific conditions and very specific set of very specific elements and compounds which are conductive to life. If we start interfering and if we start putting chemicals and things like this just randomly, life cannot exist. It's not compatible with life. So this also shows the finger of the Creator. And either also, even the compounds that are not by itself poisonous, they can be poisonous. So like the father of toxicology means the science of the poison, Paracelsus, and one of the founders of the medicine at all, the science of medicine, he said that actually the dose makes the poison. Actually, you can kill yourself with water, and we're going to study how that can happen and why it's happening. So even Paracelsus says that centuries ago, he says that the dose makes the poison. That means even if you use, he says, even if you use a non-toxic substance in a different doses, it can be toxic too. So it's not only the compounds that are not by itself toxic, but now we can see also that we need to have in the certain doses. Do you see how narrower and narrower becomes the conditions of life? And to exist, obviously, definitely, there have to be somebody that created it and make it that way. Because there is no way, whatever you do with all of these elements, all right, you cannot create life. If you take carbon, look at it. Carbon is a coal. Carbon is a coal. If you take hydrogen, hydrogen is a gas. Again, pressing too hard. Hydrogen is a gas. All right. Oxygen also is a gas. All right. Now you can, and nitrogen, which is also gas. 78% of the atmosphere, the air we're breathing, is nitrogen. It's all around. But if you combine all of these four elements and you can mix them and do whatever you want, you can never create a life. People try it, don't worry. In the 50s, and Miller tried to create life. They couldn't. And there is no way you can create a life. It's so many conditions and such a narrow set of conditions that are conducive to life. And we still don't know even what's the definition of life. You see, what is the definition of life? We still don't know it. And if we don't know what is life, how can you make it? See, that's another thing. So that's very important about the periodic table. Now you may think about why the atoms are bonding. What makes them bond? What is the force that makes them bond to have 30 million different compounds? Now, first I want to tell everything what you see around you, it's made by atoms which combine in molecules, and the molecules are bonded also together so that we can have all of these different compounds. So all of what you're seeing is the result of combinations of different atoms. All what you see. The piece of wood, the blanket, the curtain, my shirt, my body, everything is made by atoms. Now, if everything is made by atoms, there is a way that these things actually can and must bond. So to have all of these things. Now let's look at the simple molecule, the molecule of water. Now you can see that you've got two molecules of hydrogen, and you've got one molecule of oxygen, and we have two molecules of water. All right, but why they bond? Why this have to happen? Why the hydrogen and the oxygen are actually getting together, and we have the product of this unity, we've got water. First thing, there is attractive forces between atoms to create first the molecule. Let's go first to that. How the atoms get together to create a molecule, because as you can see there on the picture, We've got molecules. We don't have atoms. Look at the hydrogens. Yeah, the hydrogens are as a molecule. They are not atomic. So that why two hydrogens must get together and make a molecule. Oxygen also. Look at the molecule. Oxygen is also a molecule, not atomic. Why the atoms get combined? First thing, when atoms approach each other, the positively charged, we said what is the positively charged? You can say? Yes, protons. Attract the negatively charged electrons on the other atom. And they get together. And they start getting together. So the attraction actually lowers the energy of the system. Now, imagine I've got something in my hand. That high. If I drop it, what's going to happen? It's going to fall down. Same thing. The potential energy of something that I picked up has potential energy. It's converting to attractive and going down, converting to kinetic energy. Same thing with two atoms. When they are far apart, the positively charged nucleus attracts the negatively charged electrons, electron cloud of the other atom, and they get together. That's first thing. Second, the molecular orbitals. Now it's not atomic orbitals anymore, but now we've got molecular orbitals. Now the electrons get together and they create a cloud over the whole molecule. I'm going to show. I'm just summarizing it in the beginning, then I'm going to show. Don't worry. As atom approach, the atomic orbitals combine to form molecular orbitals. The atomic orbitals combine to form molecular orbitals. And this is called bonding. Now, it's called molecule, not anymore atoms. And these bonding orbitals are lower in energy than the original. Same thing. This is high energy. When I put the stone, it's going to fall down. This is lower in energy. So when they get combined, the atomic orbitals, which are higher in energy, get lower in energy when their orbitals get molecular. When it's get, I'm going to show a video. I'm not going to leave you just throwing you something like in the school and then after you have to read by yourself. You know very well that I care for you and I would like you to understand it. Then stability. Now when electrons are bonded in the bonded atoms, they preferentially occupy lower energy, you see, and also this preferential lowering of the energy lowers the overall energy of the whole system. Like when you hear the attractive, oh, there is energy, you want to go up, now the energy is lowered. So the electrons in the bonded atoms, they prefer this lower energy of existing. So now what's happening is that they create a new orbitals which are with less energy, and this less energy orbital is actually more stable. Like if you put something on a table or if you put something in your head, you have to balance it, otherwise it's gonna fall. Same thing like this. The electron clouds of the two atoms before bonding, they've got higher energy, like something having in your head or in your head. So they want to lower the energy, and in this way the lower orbitals are more stable. Like it's more stable something to be on the floor than to be on the table. The table, somebody can come and pick it up. It's lower energy something to be on the floor than to be on my head, say for example. You see, that's the stability. It gets more stable. And another thing is that because the bonded state has lower energy and the other one has bigger energy before, so that means if one has lower energy, the other one has bigger energy, when they bond, the energy is going to be released. You see, that's another very important thing. The energy is released. And these four things are very important to understand. We've got attractive forces, we've got molecular orbitals, which are lower in energy, then you've got stability because of this lower energy, and energy release. It's when it's released the energy, then it's also more stable. Now, let me show you something. This is another of these beautiful applications where you can access it by PHET. PHET. You can access it and you can play around. Now you've got two oxygens that are combined in a molecule, and their energy, as you can see, is the lowest. Now if we move them apart, their energy, you know, they don't feel attraction if they are so much apart. But now when they start getting near each other, as you can see, they're accelerating now. Whoop. And they go here, and if they got too near, they also bounce themselves back, you see. But the best situation is when the energy is the lowest, you see. The energy is the lowest. So we've got the forces of attraction, and also you've got the forces of repulsion. And when these forces are balanced, when the distance is certain distance, because you see, if I push the distance nearer, you can see that the energy is rising, because, you know, they repulse each other. If I get them apart with a bigger distance, you know, they are also repulsed. They are also not attracted. You see, this is the same thing like being in a good books of the president or some important man. It's good to be friend with say a president or a king or whoever it is, but it's not good to be very near to him. It's not also good to be very far from him, but it's also not good to be very near, because then it's repulsed. What's called the English proverb, familiarity causes contempt. Also with friends are like this, and with family. It's not good to be so near, because we get bounced. You see, if we get too familiar. If we get too far, also it's no good. It's not good not to call your friend. So it's good to be in a good distance, which is the optimal distance, like in this situation with two oxygen atoms, where the distance is optimal, the energy is lower, that everybody feels comfortable. So this is why they combined, as I explained the reasons. Now I'm showing you with this presentation. Now let's go back to our formula of water creation. We've got two hydrogen molecules with one oxygen molecule, and we've got two molecules of water created. Both of them are gases, and this can be a vapor, ice, or a liquid, like we normally do it. So now when we take hydrogen and we burn it, actually combine it with oxygen, then the hydrogen is combined with the oxygen and creates a water. So now you can see that the bonding now, as I explained to you before, it's with lower energy, and this is why the energy is released as a fire when you start burning hydrogen. I see. So now combining the hydrogen and with the oxygen actually lowers the energy of the two molecules, the molecule of hydrogen and the molecule of oxygen. This is why the energy is released, and it's also more stable. Now another fact I want to tell you is that, okay, combining and burning the hydrogen with oxygen is releasing approximately 268 kilojoules per mole. Right, just a figure, don't worry about it. 268 kilojoules per mole. So now to burn it, it releases energy. It releases energy simply because the energy is lower when it's combined, as we studied. Now, if you take now the water molecule and you want to turn it back now to hydrogen and to oxygen, do you know how much energy you need? You need 4 times more energy, almost. 928 kilojoules per mole. Mole means unit, as I said to you, 6.022 by 10 on the 23rd power. That's mole. So to convert 1 mole of water vapor to hydrogen and to oxygen, you need 928, while the other one you need 206, almost 268 kilojoules per mole. So that means you can see now, it's much difficult now to break the molecule, this molecule, than to create it. That means this is more stable. As it is much difficult to pick a stone from the ground than to drop it. You see, so now exactly the same here, it's much difficult to break the molecules because there is forces that are holding it now. This electromagnetic force that are holding it and sharing the electrons and all of this that we explained. So this is why the atoms actually bond, because their energy level is getting lower. Now let me show you this in practice. Now we've got two probes with different electrodes, and both of them are filled with water, and we've got the positive terminal and we've got the negative terminal. All right, so now we put electricity, we connect it with electricity. We can put some sulfuric acid, very little sulfuric acid or salt, to make the electrolysis better. But now you can see, as soon as we put electricity, we got energy to break the molecule. Now we're getting gases, and these are the gases, hydrogen and oxygen. Now you can see they start bubbling from the electrodes. You see. So this is how we actually, this is called electrical dissociation. We dissociate the water in its compounds that are in its atoms that are connected in its molecules, the hydrogen and the oxygen. Now I'd like you to tell me now, where is the oxygen and where is the hydrogen? Now think about, where is the hydrogen and where is the oxygen? Now, you know the formula H2O, and gases, I'll give you a clue now, the gases at room temperature, 1 mole of gases is always 22.5 liters. Every gas, the oxygen, nitrogen, even the heaviest gas like a radon, it's not on my name though, helium, and all other gases, all of them at room temperature have volume of 22.5 liters. Why is this? Because the molecules are very far apart, and because they move around, so they take only this volume. All right, they've got this volume, and now you can see one of the volumes is 2 times and the other one is 1 time. So I want you to tell me now, where is where? All right, did you guess it? Of course, you've got 2 atoms of hydrogen and 1 atom of oxygen. This is why on the right probe we've got 3.5 cubic centimeters, and the other one we've got 7. You see now, you can see actually now what we studied previous lecture, now we prove it with electrolysis. Now you can see that the atoms are the same ratio, the law of constant proportions and the law of definite proportions. You see, so that's actually the case that we proved. All right, so you can see the atoms are existing, but just by this experiment you can see that the formula is corresponding to the experiment. Okay, so now we saw that it takes 968 kilojoules per mole. It's much less than a mole here. Where is 22 liters? Where is 7 cubes? Right? 22 liters is 22,000 cubes. It's a different story. We've got here 6-7 cubes. And now we see that when we try to dissociate the molecule, we've got so much energy needed to actually break the molecule into its constituents, hydrogen and oxygen. Now let's see what's going to happen when we have combined the hydrogen and with the oxygen. Let's see what is going to happen. What you see here is the Zeppelin Hindenburg is flying from Frankfurt am Main 1937 to New Jersey, USA. It's full with hydrogen. Hydrogen can be dangerous, and you're gonna see why. And normally balloons and things like this normally are filled with helium or with hot air, which is lighter and less denser than the other air, so this is why it flies up. And helium is also less denser than the air. This is why helium balloons, are filled with, for the children, they fly. And if you drop it out, it's gonna go. Now, but the Germans didn't have helium, so they put hydrogen. And you can see it's flying, and it's flying quite well. Although not like the airplane, but it's flying. It's getting well. Now, what's happening? During the flight, it got static electricity. And this static electricity caused fire. And fire with hydrogen, we know what's happening. Hydrogen takes a little spark, a very little spark, to start burning and combining with the oxygen. You see, the energy it releases is 268 kilojoules per, it's per mole, and this causes fire. And they are ready to combine hydrogen and oxygen. They are ready. Just need a little spark. It's called activation energy. So it's actually a tragic event, which it happens. Look at it now. It is just terrible.
The German Zeppelin Hindenburg, queen of the skies, seen here from a Universal newsreel camera plane as it sped over New York to its tragic end at Lakehurst, New Jersey, now lies at the Naval Air Station a twisted mass of metal. Shortly after these pictures were taken, showing the great Skyliner saluting the millions watching it from below on its first trip of the season, the huge craft exploded while docking and blazed to a fiery end, taking the lives of almost half its 99 passengers and crew. Hours late on its trip from Hamburg because of headwinds, the Zeppelin had to ride out a thunderstorm along the Jersey coast before heading for the air station and nosing its way to the mooring mast. The wind is bad and the docking is a ticklish one, but it's all a thrill for the crowd of happy passengers eager to land after their transoceanic trip. Slowly the big ship warps in, and the ground crews rush for the mooring line. In another 10 minutes or so, the great aircraft would have been snugly docked. But as the passengers crowded the windows to watch, a roar and a burst of flame near the big tail fins turned the ship into a flaming inferno. Passengers and crew, the fortunate among them, fell or jumped and were dragged to safety before the fiery furnace took their lives. Heroic work by Navy and Army men risking their lives around the white-hot skeleton. The German Zeppelin.
What happened is people died. Now I can say, hey, all of them died. No. By miracle, 36 people is the total number of casualties. 62 survived. One man on the ground was also killed. And it's a tragic event, but you can see the energy released when hydrogen and oxygen from the air get together. They release energy. Because combined, their status is with lower energy. And it's tragic that so many people died, but this is what actually the chemistry is teaching us, that when you combine hydrogen and oxygen, you're gonna have lower energy, and then this lowering of the energy is the release of the energy. Thank you very much for your attention, and I hope I'm going to see you next time.